Okay, so so you see, let us recall what we did in the last lecture. See, just to fix up also the notation. So we started with tau in the upper half plane, okay, the set of all complex numbers with the imaginary part positive, yeah, and then associated to tau the lattice L of tau, which is a set of all m plus n tau, where m and n are integers, and then we have the torus associated to tau, the complex one dimensional torus associated to tau, which is just C mod L tau, and we are able to get hold of the essentially the unique the simplest meromorphic function on the torus, which is given by the Weierstrass phe-function on the complex plane, which is given by phi sub tau of z. It is given by explicitly by a formula of this form. So the summation over, so it is 1 by z squared, which is the singular part at the origin, that is a normalization that makes this function unique. Then you sum over 1 by z minus omega the whole squared minus 1 by omega squared, we got the phi function, and then we then notice that the phi function satisfies a differential equation, which is I guess p sub tau the whole prime the whole squared is 4 p sub tau 4 p tau cubed minus g2 of tau p tau minus g3 of tau. This was the differential equation that was satisfied by the Weierstrass phi function and its derivative. Of course, the variable here is the independent variable is z, okay, but there is also dependence on tau, and which is what we used to define the modular function lambda. So if you recall, we factorize the right side as p tau minus e1 into p tau minus e2 into p tau minus e3, and where you know so e1 is actually e1 of tau is actually p tau of half, e2 is e2 of tau is p tau of tau by 2, and e3 is also dependent on tau, it is p tau of 1 plus tau by 2, and then we noticed that with the function lambda of tau, which is given by I think it is e3 minus e2 by e1 minus e2, if I am not mistaken, yeah, so it is e3 minus e2 by e1 of tau minus e2 of tau, we got this function, and what we proved last time was that this function lambda, which is a holomorphic function on the upper half plane, is invariant under elements of PSL to Z, the unimodular group, which are congruent to the identity matrix when the coefficients are read mod 2, okay. So this is what we proved last time, and so you see all this was towards the objective of trying to find a function on the upper half plane which is an invariant for the tori. That means a function which is constant on orbits of PSL to Z for its action on the upper half plane, and you know these orbits are precisely the holomorphic isomorphism classes of complex tori. So so far we have had partial success because this is only a subgroup. It's a normal subgroup of the full unimodular group. So you have to somehow from this automorphic function, from this modular form, you have to cook up a modular function which is modular for the full unimodular group, okay, and that is the one that is going to be constant on the orbits for the action of the full unimodular group. So how does one do that? One cannot do that unless, of course, you know, the natural thing is that one has to study how lambda is affected by an arbitrary element of the full group, the full unimodular group. So you see, so in fact the aim of this lecture is to show that lambda satisfies certain functional equations, okay, and these functional equations tell you exactly how you can compute the effect of any element of the full unimodular group on lambda, okay. So how, of course lambda is not invariant under the full unimodular group, okay, so but so it changes, so one wants to know how it changes, okay. In other words, what I mean is, you see, you change tau by a unimodular transformation, okay, then the lambda of tau will change. It will no longer be it will no longer be lambda tau, unless of course that element is congruent to identity mod 2, okay, which we have proved, okay. So for if you take a general unimodular element, if you apply it to lambda, what is the effect? If you apply it to tau, what is the effect of that? What is lambda evaluated on that? That's what we want to calculate, and then it turns out that it can be done in a very nice way. So essentially the first part of the argument is that you should notice that, if you recall, so you take PSL 2Z, okay, there is this group homomorphism, there is a group homomorphism which is simply take a representative here, which is a 2 by 2 matrix with determinant 1 with integer entries. The representative is unique up to sign, okay, and then you read each entry mod 2, okay. So the result is you will get an element of the unimodular group with coefficients in z mod 2z, okay, which is just 0 or 1. Z mod 2z is just 0 or 1, is the smallest field that we know, and well, in fact this is the same as because plus 1 is equal to minus 1, this is the same as SL2 Z mod 2 as well, okay, and so and of course this map is of course surjective trivially, and the kernel of this map is precisely this congruence mod 2 subgroup, okay. So kernel of phi 2 is exactly the congruence mod 2 subgroup, which under which we know, we have proved is in the last lecture that lambda is invariant, okay. Now you see, now you just take, okay, so let me write this, recall, this is a normal subgroup, of well PSL2C, the unimodular group, okay, and if you calculate, so you know, if you calculate PSL2Z PSL2Z mod 2Z, if you calculate this I mean this is essentially if you write down the transformations, you will essentially get 6 matrices, okay, and what are those 6 matrices? Let me write them down. So I'm just trying to write it in a certain order that I have written for myself, so of course maybe I'll write it here. So it is of course you have the identity matrix, then you have the matrix 1 1 0 1, then you have the matrix 0 minus 1 1 0, okay. Then you will have 1 minus 1 1 0, you will have 1 0 1 1, and the last one is 0 1 minus 1 1. You will get these matrices, okay. So I mean, of course, you know, here wherever there is a minus 1 I can put a plus 1, it is not going to make a difference because the coefficients are mod 2, but the point is I am putting minus 1 is because I can use the same matrix as an element here which goes to that, okay. And the reason why I put this minus in these 3 places has a significance, because after all these are Mobius transformations, okay. Because you see, if you notice, let me call, of course, you know, I have so let me call these matrices as well A1 etc. A6 in the order written, okay. Let me call, so I am calling this as A1, this is identity matrix, this is A2, this is A3, A4, A5, A6, okay, and these are all the matrices that you have, okay. And in fact and of course I will also think of the AIs also as matrices here, okay. That is, each of these matrices which you consider as matrices here are also matrices here, their pre-images, chosen pre-images which go there, okay. That is the advantage of looking at it like this. And when I write it here, these signs matter to me, because here 1 is not equal to minus 1, okay. So now you see take so you know, the question is the following. The question is you want to, from lambda you want to cook up a function which is invariant under the full modular group. So the question is, how is lambda going to be affected by an element of a general element of the modular group, the full unimodular group. So you see, if A is an element of the full unimodular group, what is lambda of A tau? Can you compute this in an easy way, okay. So the question is, I want to know how lambda is affected if I twist it by an element of the general unimodular group, okay. So see, the answer is that, well, you see, take the image of A under phi2. So A is here, you take its image here, then this image is going to be exactly one of these AIs, okay. So you see, so phi2 of A, suppose it is AI, okay. Of course this is going to be for a unique I, okay, for a unique I, alright. Then what does this mean? In fact, you know, I can also write as phi2 of AI, okay. Here there is a slight abuse of notation, I am just saying that I am taking the same AI as a representative here which goes to that, okay. So what does this mean? This means that, you see, these two go to the same, so it means that, you know, phi2 of AI inverse A, which is equal to phi2 of AI inverse, will be phi2 of so it will mean that well, because phi2 is a homomorphism, you know, this will mean that this is equal to phi2 of identity, which is identity map. And what this therefore tells you is that you know, AI inverse A and well you see and AI inverse, see they are all, they both belong to the kernel of phi2, okay, because they are mapped by phi2 into onto the identity, and you know the elements of the elements here that go to identity there are precisely the kernel of phi2, and that is the congruence mod 2 subgroup, okay. So but we have already proved that the effect of the lambda is invariant under the effect of elements of the congruence mod 2 subgroup. So you know, so what you will get is you will get lambda of AI inverse A of tau is lambda tau, and you will also get lambda of AI inverse tau is lambda tau, okay. So therefore the you know for example my aim is to calculate what lambda of A tau is. So you know in this, for example in this second equation, for example suppose I replace AI inverse tau by some tau prime, okay, then I will get lambda of A tau prime is equal to lambda of AI of tau prime, okay. So you know, so if we set let us say AI inverse of tau as tau prime, okay, mind you all these AIs are elements in PSL2Z which is a subgroup of PSL2R, and these are certainly automorphisms of the upper half plane. So therefore AI inverse of tau is also going to be an element in the upper half plane, okay. So you see what you will get is that you will get that lambda of A of tau prime is from here, you see AI inverse tau is tau prime, so I will get lambda of A of tau prime is lambda of tau, but tau is AI of tau, okay. So you see we have the answer to our question, tau prime, okay, and well, or if you forget, if you continue, if you want to call tau prime as tau, you can in general say that this lambda, so let me not do that just to avoid any confusion. What this equation tells you is you want to compute the effect of an element A on lambda, it is enough to compute the effect of you read that element mod 2 and compute the effect of that on lambda, that is all, that is what it says, okay. Now but you see these transformations are all very nice transformations. So you see A1 tau is just tau, you see A1 tau is just mind you whenever we write an element alpha beta gamma delta, alright, then it is thought of as a Mobius transformation that takes z to alpha z plus beta by gamma z plus delta, okay, that is the identification. So you see A1 of tau is going to be just tau, okay, A2 of tau is going to be, you can see it is tau plus 1, okay, A3 of tau is simply minus 1 by tau, okay, and then A4 of tau is tau minus 1, and A5 of tau is tau by tau plus 1, and A6 of tau is tau by minus tau plus 1, so it is minus so it is tau by, so it is 1 by minus tau plus 1 which is 1 by 1 minus tau, okay. So these are the simple Mobius transformations. So A1 tau is this identity, A2 tau is translation by 1, okay, A2 tau is translation by 1, A3 tau is minus 1 by tau, okay, A4 tau is translation by minus 1, so is there, so A4 tau is tau minus 1 by tau, okay, so it is tau minus 1 by tau, yeah, it is tau minus 1 by 1 into tau plus 0, and a phi tau is tau by tau plus 1, and a6 tau is 1 by 1 minus tau. And so you see you are just required to find out what is the effect of lambda on one of these, okay, and then you will be able to say what is the effect of effect of any general unimodular transformation on lambda, okay, that is what you have to. So this question reduces our computation to the computation of these things, okay, and computing these things actually give us certain equations, certain relationships between lambda applied on tau and on these things, the images of tau under these maps, which are called functional equations. So that is so in fact we get 5 functional equations, okay, of course the first one is trivial, there is nothing to do here. So we get 5 functional equations, and all these 5 functional equations can be derived by 2 basic functional equations, and these are the functional equations that involve a2 and a3, okay. So there is something that I want you to notice, that you see if tau is in the upper half plane, then 1 by 2 isn't, but minus 1 by tau isn't, but minus 1 by tau is, okay, and similarly you can verify that all these guys are certainly in the upper half plane, okay. So obviously if tau is in the upper half plane, tau plus 1 is, and so you can calculate this, okay. Tau plus 1 is, minus 1 by tau is, so this is 1 minus 1 by tau, which is translate of minus 1 by tau by with 1, so that is also there, okay, and so on and so forth. You can justify that these guys are all continue to be in the upper half plane, I mean which is just the fact that these are all automorphisms of the upper half plane, so they have to be, the images of under tau have to be in the upper half plane, okay. So you see now so we need to just compute lambda of ai of tau for 1 less than for 2 less than or equal to I less than or equal to 5, 2 less than or equal to I less than or equal to 6. You have to compute only these quantities, okay. Now so here is the we have so let me write this down, theorem. So you have the following, so let me write this down. Number 1, lambda of a2 of tau is lambda of tau plus 1, that turns out to be lambda tau by lambda tau minus 1, okay. So you get all these functional equations, mind you lambda, the function lambda never takes the function lambda on the upper half plane actually never takes the value 1, it never takes the value 0, therefore this division by lambda tau minus 1 is never going to create a problem, okay. The second one is lambda of a3 tau is lambda of a3 tau is minus 1 by tau, and that turns out to be 1 minus lambda tau, okay. Third one, lambda of a4 tau is lambda of tau minus 1 by tau, which is 1, it is lambda tau minus 1 by lambda tau, okay, and lambda of a phi tau is lambda of a phi tau is tau by tau plus 1, that comes out to be simply 1 by lambda tau, okay, and the fifth one is lambda of a6 tau comes out to be 1 by 1 minus lambda tau. So this is lambda of minus lambda of A6 tau is 1 by 1 minus tau. That just turns out to be 1 by 1 minus lambda of tau. So, so these 5 together, they are called functional equations of lambda, because you see the same function with the difference in the arguments, there is a relationship. So these are all functional equations. So these are called functional equations satisfied by lambda. Okay. So in fact, so not only does this answer this question, but the fact is these Mobius transformations will help you to single out a certain special region of the upper half plane, studying which along with the mapping properties of lambda, you can build a modular function which is modular on the whole unimodular group. Okay, so these Mobius transformations are also important. So we will see that in the forthcoming lectures. So you see, the fact is that we only need to prove 1 and 2, okay, because you see the others 3, 4 and 5 can be deduced from 1 and 2, okay. 3, 4 and 5 can be deduced by because you see lambda of tau minus 1 by tau is lambda of 1 minus 1 by tau, so it is lambda of minus tau plus 1 minus 1 by tau plus 1, so it will be lambda of minus 1 by tau by lambda of minus 1 by tau minus 1, and then you use lambda of minus 1 by tau is 1 minus lambda tau, okay. So actually 2, 3, 4 and 5 are a consequence of 1 and 2, okay. So proof 3, 4 and 5 are a consequence of 1 and 2 applied diligently. So we only have to prove 1 and 2, okay. So we only need to prove 1 and 2. Well, I hope that these formulas are right, because I wrote them down once. Okay, so now the point is the following. The point is how do you prove them? So well, to prove them, I am again going to go back to this piece of computation that I used in the last lecture, which I have borrowed from lecture 24, which is which essentially comes from the question, from the statement that the complex tori defined by two elements in the upper half plane are holomorphically isomorphic if and only if the two elements in the upper half plane differ by a unimodular transformation. So let me again recall that that calculation. It seems to be indispensable. So you see recall, you see if we have tau 1 and tau 2 in the upper half plane, okay, then the existence of a Mobius transformation B of the that takes the complex plane onto itself, okay, which maps L of tau 1 isomorphically onto I should let me not say isomorphically, I should let me say bijectively onto L of tau 2, okay, is equivalent to the existence of a holomorphic isomorphism f from the complex torus defined by tau 1 to the complex torus defined by tau 2, okay, and is also equivalent to the existence of a unimodular element which gamma delta alpha beta in PSL2C, okay. So I am unfortunately still writing gamma delta alpha beta because I messed it up in lecture 24, but really it shouldn't matter, such that gamma tau 1 plus delta by alpha tau 1 plus beta is tau 2, okay. So this is something that we use indispensably, okay. So in fact let me write out, let me again recall what this B was. So in fact the situation was that we have this Mobius transformation B which goes down to the complex torus defined by tau 1, namely T sub tau 1, and it goes down to an isomorphism, holomorphic isomorphism of T tau 1 to T tau 2, which is C mod L tau 2, and this is the projection which is a holomorphic universal covering. And we notice, I mean if you recall, B of Z, B had the matrix B, the matrix of B was given by A 0 0 1 by A, okay. So B of Z was just A squared times Z, okay, and of course B of 1 was A squared, and B is therefore additive, and it takes the lattice defined by tau 1 bijectively onto the lattice defined by tau 2. And what is this A squared? In fact if you calculate B of 1 turns out to be A squared, which is it is 1 by alpha tau 1 plus beta, and that turns out to be minus alpha tau 2 plus gamma, and you can see that B of tau 1 turns out to be beta tau 2 plus beta tau 2 minus delta, okay. This is the, I mean this is how B is if you calculate, okay, and this clearly tells you that B takes, and since B is additive because it is just multiplication by a scalar, by a complex number, complex constant, so B is additive, and it will tell you that therefore any linear integer linear combination of 1 and tau 1 is going to land into the lattice defined by 1 and tau 2, okay, and because it has an inverse, this has to be a bijective map, okay. B is a Mobius transformation, you know Mobius transformations are already injective, okay. So yeah, so now you see, and then you know in fact I mean what is the point? The point is, you see, if you write if we take see you take tau 1 as a basis for L tau 1, and tau 2 comma 1 as a basis for L of tau 2 over, of course, all over Z, okay, then actually B, you restrict B to L tau 1, you get a map, you get a bijective map onto L tau 2, that's it's a Z module map, and if you write the matrix of that map, that matrix is just related to this matrix, this unimodular matrix in PSL2C, and what is it in fact, then you see the matrix of B is just it turns out to be just that matrix gamma delta alpha beta well transpose inverse, which is just you know beta minus alpha minus delta gamma. Okay, so because you see B of tau 1, B of the first basis vector B is B of tau 1, that gives you beta comma minus delta, which is the first column, and B of the second basis vector B1 gives you minus alpha gamma, which is the second column. So this is exactly this. So the matrix of B, so when I say matrix of B, you restrict B to the lattice, you restrict B to the lattice L tau 1, you get a bijective map onto the lattice L tau 2, that's a Z linear map. So it is given by matrix with Z entries, and it's a unimodular matrix because this is an invertible, the determinant is an invertible integer, and because tau is in the upper half plane, you know that it cannot be -1, we proved that. So in fact this is the relationship, so this is actually that matrix, its transpose inverse is actually the matrix of B relative to these bases when you restrict B to the lattice. Okay, so then we proved in the in the last lecture that there is a kind of there is an equation which tells you how the phi function is transformed if you keep the I mean if you apply you know, if you apply I mean what is the relationship between the phi function that is defined for tau 1 and the phi function that is defined for tau 2 if tau 1 and tau 2 are related in this way. So in fact what we proved is that we proved that we proved in the last lecture that, and I need this, B of 1 the whole squared p tau 2 of B of z is equal to p tau 1 of z. We proved this. Okay, so we proved this last time, and this is very easy, I mean this is very easy to prove just using the direct expansion of the phi function and using the fact that B of z is z times B of 1, okay, and also using the fact that B maps L tau 1 onto L tau 2 and it takes non-zero elements of L tau 1 exactly onto non-zero elements of L tau 2. Okay, so it was very simple to prove this, and let us write it out in terms of these alpha beta gamma deltas. So you see what it will tell you if I write it down is I'll get p tau 2 of Bz is z times B of 1, B of 1 is a squared and a squared is, so it will be B times z by alpha tau 1 plus beta is equal to and I push this B of 1 whole squared to the denominator so that I get 1 by B of 1 the whole squared, and that will be 1 by a squared, and that will be alpha tau 1 plus 1 by a squared the whole squared, so it will be alpha tau 1 plus beta the whole squared. So here I will get alpha tau 1 plus beta the whole squared into p tau 1 of z. Okay, so yeah, so this is what I want to use, I need to use this. So so let's well let's now let us calculate this. So let's try to prove to show the first formula. Okay, so I just want to calculate lambda tau plus 1 in terms of lambda tau. So you see what I do is and you see that A2 takes tau to tau plus 1, so basically I take tau 1 as tau and tau 2 as tau plus 1. Okay, notice that if I take A2 of tau is tau plus 1, tau 2 is A2 of tau. Okay, and the point is I should take for A2 this this unimodular element, see I have to take the unimodular element that takes tau1 to tau2, okay. So as I was thinking for a moment, one should not get confused with the b there, okay, one should not get confused with the b there. So well, you see tau2 is A2 of tau, which is A2 of tau is tau plus 1, okay, and if you do this, then what you will get is you will get p tau plus 1 of z divided by so you see our so here my A2 is what is A2, it is the matrix A2 is well, it is 1 1 0 1, okay. So it is a matrix 1 1 0 1, okay, and I have to compare this with gamma delta alpha beta, okay, okay. So you see so if I apply this formula here, I will get z by alpha tau 1 plus beta is going to be 0 tau 1 plus 1, so it will be 1 is equal to 0 tau 1 plus 1 the whole square, that is going to be just 1 squared into p sub tau 1 is just tau of z. So I mean finally you get that p tau plus 1 of z is just p tau of z, okay. So p sub tau plus 1 of z is simply p tau of z, okay, it's simply p tau of z, okay. And now calculate what is the corresponding EIs are, okay, because the lambda is different based on the EIs, okay. So if you want to check how lambda changes, you have to check the way EI changes. So in fact what you will get is, so let me directly write this, lambda of tau plus 1 is, mind you, it is E3 of tau plus 1 minus E2 of tau plus 1 by E1 of tau plus 1 minus E2 of tau plus 1. I mean this is how lambda tau is defined, lambda tau is E3 of tau minus E2 of tau by E1 of tau minus E2 of tau, that is how lambda is defined. And you see, but you see what is E3 of tau plus 1, it is p E3 of tau is just p tau applied to 1 plus tau by 2, okay. So this E3 of tau plus 1 is p tau plus 1 applied to 1 plus tau plus 1 by 2, okay, and E2 of tau plus 1 will be p tau plus 1 applied to so E2 of tau is p tau applied to tau by 2, okay. So this will be p tau plus 1 applied to tau plus 1 by 2, okay, and E1 of tau is p tau applied to half, so E1 of tau plus 1 will be p tau plus 1 applied to half, okay, and E2 of tau is again p tau plus 1 applied to tau plus 1 by 2, this is what you will get, okay. But then you use the fact that p tau plus 1 is the same as p tau, okay. So what I will get is I will get p tau of, well, if I will get 1 plus tau by 2, okay, minus p tau of 1 plus tau by 2 whole by 2 by p tau of half minus p tau of 1 plus tau by 2, and you can recognize that, you see, p, of course p tau, the phi function is periodic with respect to 1 and tau. So you see p tau of 1 plus tau by 2 is p tau of tau by 2, and p tau of tau by 2 is E2 of tau, okay. So this is E2 of tau and that is E3 of tau divided by E1 of tau minus E3 of tau, okay, and you can clearly see that this is you know what I want is lambda tau by lambda tau minus 1, this is in fact well, it is very easy to see that it is E3 of tau minus E2 of tau by E1 of tau minus E2 of tau divided by the same quantity E3 of tau minus E2 of tau by E1 of tau minus E2 of tau minus 1, because if you simplify this you are going to get E3 minus E2 on top, that is the same as this up to a sign, and denominator you will get E3 minus E1, which is the denominator up to a sign, so you will get this. So you will get therefore that lambda tau plus 1 is lambda tau by lambda 2 minus 1, which is the first functional relation. Okay, so let me write that down. So you will get so we get, and that turns out to be lambda of tau by lambda of tau minus 1. So 1 is proved. Okay, literally the same kind of exercise, if you carry it out, you can prove the second one. Okay, so let me write that down. So for the second one, so to show 2, take again, so if you look at 2, so you see the transformation that I have to take is A3. Okay, it takes tau to minus 1 by tau, so I will take tau as tau 1 and I will take A3 for this transformation. Okay, so that when I apply tau to it I get minus 1 by tau, which will be tau 2. Okay, so you take tau 1 is equal to tau, A3 is equal to, which is A3 is just so it is 0 0 minus 1 1 0. Okay, which has to be compared with gamma delta alpha beta. Okay, and so tau 2 will be just A3 of tau 1, which is A3 of tau, which is A3 of tau is minus 1 by tau, so tau 2 is minus 1 by tau, and then you apply. So let me rub this off. Well, and then you literally do the same thing. You again apply this formula. Okay, I mean this formula, right? So you will get P sub tau 2, which is minus 1 by tau of Z divided by alpha tau 1 plus beta. So alpha tau 1 plus beta is going to be 1 into tau plus 0. So I am going to get Z by tau is equal to again alpha tau 1 plus beta is going to be 1 into tau plus 0, so that is just tau squared into P sub tau 1, which is tau, and of Z. Okay, and for convenience I can write this as P of minus 1 by tau of Z is well, you know, if I replace Z by tau by Z, then I have to replace Z by Z tau, so this will become tau squared P tau of tau Z. Okay, and now go through the now you go through the same computation. You calculate what is lambda of minus 1 by tau. Okay, you calculate what is lambda of minus 1 by tau. It is by definition E3 of minus 1 by tau minus E2 of minus 1 by tau divided by E1 of minus 1 by tau minus E2 of minus 1 by tau. Okay, and well, now I make use of the fact that E3 of minus 1 by tau is P of minus 1 by tau applied to E3 is P tau applied to 1 plus tau by 2, so it is 1 plus minus 1 by tau divided by 2. Okay, minus E2 well, E2 of tau is just P tau applied to tau by 2, so this is going to be P of minus 1 by tau applied to minus 1 by tau by 2. Okay, divided by, I will get again here I will get E1 of tau is just p tau applied to half. So this is going to be p of minus 1 by tau applied to half, and here again I am going to get p of minus 1 by tau applied to minus 1 by tau by 2. Okay, this is what I am going to get, and now I make use of this formula that I have derived, and we will get what we want. In fact, we will get, so let me write that down. So we will get that is equal to let me write down what is on the left side. Lambda of minus 1 by tau is equal to, well, p p minus 1 by 2 of z is just tau squared p tau of tau z. So I will get tau squared p sub tau of tau times z. So I have to multiply this whole thing by tau. If I multiply this by tau, I will get tau minus 1 by 2 minus, again I will get tau squared p tau of multiplying this quantity inside by tau, I will get minus half divided by tau squared p tau of multiply the quantity inside by tau, I will get tau by 2 minus tau squared p tau of minus half. Okay, and then you have to now remember that I can add 1 to this, and this becomes p tau of 1 plus tau by 2, which is E3 of tau. Okay, of course the tau squares will cancel throughout, you can take tau squared common numerator and denominator, that will just go away, and p tau of minus half is the same as p tau of half because I can add 1, and it is periodic with period 1, and p tau of half is E1. So and p tau of tau by 2 is anyway E2. So what you get is you get actually E3 of tau minus E1 of tau by E2 of tau minus E1 of tau, and this will turn out to be what you want, which was, well, I rubbed it out, it is this is 1 minus lambda of tau, so it is 1 minus E3 of tau minus E2 of tau by E1 of tau minus E2 of tau. Okay, because if I simplify this, the numerator I will end up with E1 minus E3, and denominator I will get E1 minus E2, so which is just 1 minus lambda of tau. Okay, so so similarly you can manipulate these things to get the other functional equations. Okay, so so that finishes, so that answers the question as to how lambda behaves if you try to apply an arbitrary element of the unimodular group to the argument of lambda. So it gives all these functional equations. Okay, so in tomorrow's lecture, I mean in the next lecture, we will see how all this data can be used to study the mapping properties of lambda. Okay, and studying these mapping properties will help us to single out a certain special domain in the upper half plane, on studying which you can cook up a function which is modular for the full modular group, and which is going to be the elliptic modular function, and that is the invariant we are looking for. Okay, so so we will see that in the next lecture.